Somewhere off the coast of Vancouver Island, a 75-kilometer crack running along the ocean floor has gone quiet. And in earthquake science, quiet is usually the part that should actually worry you. Stick around, because by the end of this video, you'll understand exactly why a magnitude 5. 6 earthquake that didn't hurt a single person is being taken this seriously by the scientists who study this region. What actually happened Sunday night at 11:41 p.m. on Sunday, Pacific time, a magnitude 5. 6 earthquake broke open the seafloor west of Vancouver Island. The United States Geological Survey placed the epicenter roughly 129 miles southwest of Port McNeill, British Columbia, at a depth of about 10 kilometers, just over 6 miles down. Earthquakes Canada, working from a slightly different reference system, placed it about 219 kilometers southwest of Port Hardy, at the northern tip of Vancouver Island, at almost the same depth. A more detailed follow-up analysis later placed the source a little deeper still, closer to 11 or 12 kilometers beneath the seafloor. Nobody was hurt, no buildings were damaged. Earthquakes Canada stated plainly that there was no tsunami risk, and no agency issued any kind of warning or advisory. On paper, this looks like a complete non-event, the kind of quake most people would forget about by lunchtime the next day. But it isn't being treated that way, and the reason has almost nothing to do with how large the earthquake actually was. It's about exactly where it happened. This magnitude. 5. 6 struck inside the single most structurally complicated section of the entire Cascadia Subduction Zone, a stretch of ocean floor that scientists only managed to properly image in real detail for the very first time less than a year ago. And what that imaging revealed is that this particular patch of seafloor is actively tearing itself apart. Now, that's really the actual headline here, and it's a lot more specific, and honestly a lot stranger, than simply asking whether the big one is finally on its way. Felt far wider than expected. People felt this earthquake far beyond the range you'd normally expect for something this size. Shaking was reported across northern Vancouver Island and all the way out to Metro Vancouver, more than 450 kilometers to the southeast. Reports also came in from parts of western Washington state, including Seattle. Campbell River, roughly 300 kilometers from the epicenter, felt it clearly. So did Port Alberni, about 330 kilometers away. That's an unusually wide footprint for a magnitude 5. 6 sitting at this particular depth. It tells you something meaningful about the type of rock this rupture happened inside of. Cold, dense oceanic crust carries seismic energy very efficiently, allowing waves to travel hundreds of kilometers through it, and still arrive strong enough for people to clearly notice, quite different from how that same energy would get absorbed and scattered while moving through warmer, more fractured continental rock on land. Why nobody got hurt? This time, the reason nobody actually got hurt, though, comes down to something much simpler than wave physics. This earthquake happened out in the open ocean, more than 200 kilometers from the nearest town. On Saturday, a magnitude 5. 5 earthquakes struck near Sequani in Peru's Cusco region at a similarly shallow depth of about 10 kilometers. It killed at least 6 people, injured more than 30, and displaced roughly 300 residents. It also collapsed a historic church and former convent in Chekakup that had stood since 1565. Local officials pointed to the widespread use of traditional adobe construction in the area as a major factor behind how much damage occurred. Same rough magnitude, same rough depth. 6 people dead in one case and 0 in the other. The real difference wasn't the underlying seismology at all. It was what happened to be built on top of it, and exactly where it was built. Keep that direct comparison in mind, because it matters quite a bit for how we should think about earthquake risk later on in this story. Reading the fault's fingerprint. Within hours of any significant earthquake, seismologists put together something called a moment tensor solution, often casually nicknamed a beach ball, because of how the resulting diagram looks. A sphere split up into alternating black and white sections. It tells researchers the geometry of the specific fault that broke, and which direction the two sides of it actually slid against each other. For Sunday's earthquake, the data pointed toward 2 possible fault planes, both extremely steep, one dipping around 77 degrees and the other around 86 degrees, nearly vertical. And the overall motion was overwhelmingly strike-slip, meaning the 2 blocks of oceanic crust slid sideways past one another, similar to how the San Andreas Fault typically moves in California, rather than one plate riding directly up and over the other. Compare that to what happens during an actual Cascadia megathrust earthquake. In that kind of event, the oceanic plate suddenly thrusts underneath North America along a broad, shallow-angled surface stretching hundreds of kilometers. That particular kind of geometry is exactly what lifts or drops massive sections of seafloor all at once, and it's that vertical shove of the entire water column sitting above it that actually generates a tsunami. A steep, sideways sliding rupture, by contrast, barely displaces any water at all. This is exactly why Earthquakes Canada was able to rule out tsunami risk with real, genuine confidence, not as some kind of routine boilerplate disclaimer, but because they read it directly off the underlying rupture mechanism itself. A fault dipping at 86 degrees and sliding sideways simply isn't built to lift the Pacific Ocean. Was this the megathrust starting to fail? So here's the frightening question everyone naturally jumps to. Was this the megathrust fault finally starting to fail? The data gives a pretty clear answer, and that answer is no. Those two numbers, 77 and 86 degrees, are actually the single most reassuring figures in the entire report. What the data genuinely can't tell us is exactly which fault broke. The epicenter sits somewhat west of the main mapped fault zone in this region, and a beach ball diagram alone simply can't pin a specific rupture to one particular named structure. Why the northern tip of Cascadia is so messy. To really understand why, you need to know what's actually happening at the very northern tip of the Cascadia system. Most simplified explanations of Cascadia keep things fairly basic. One single oceanic plate sliding beneath one continental plate, along roughly 100 kilometers of boundary, converging at somewhere around 40 millimeters a year. That simple description works reasonably well for the middle section of the margin. At the northern end, though, it falls apart almost completely. The incoming oceanic plate near Vancouver Island isn't actually one single unified sheet of rock. It's really made up of three separate pieces. The Juan de Fuca plate sits in the center. The Gorda plate sits down at the southern end, and right at the very north, there's a small microplate called the Explorer plate. And the Explorer plate is in real, genuine trouble. It's being squeezed and sheared from multiple directions all at once by the Pacific, Juan de Fuca, and North American plates surrounding it on every side. It subducts far more slowly than its much larger neighbor. Where the Juan de Fuca plate moves toward the continent at roughly 4 centimeters per year, the Explorer plate manages only about half that rate, and some sections appear to be moving even slower still. Some published research has even suggested that parts of the Explorer segment may not actually be effectively subducting at all anymore. When a plate can no longer move as one piece, here's really the mechanical heart of this entire story. When different sections of a single tectonic plate start moving at noticeably different speeds and in different directions, that plate simply cannot continue behaving as one solid, unified block anymore. It's forced to deform internally instead, bending, twisting, and shearing under the competing forces acting on it. And a rock plate forced to deform that way tends to do it by repeatedly breaking along steep internal fractures, exactly the kind of near-vertical, sideways sliding motion this particular earthquake displayed. Separating the Explorer plate from the Juan de Fuca plate is a structure geologists call the Nootka Fault Zone. It formed roughly 4 million years ago, when the Explorer Ridge split off and became fully independent from the Juan de Fuca Ridge, and it's been steadily absorbing sideways motion between the two ever since. Published research has shown that this original split was never a clean, tidy break to begin with. It started out as a genuinely messy zone at least 80 kilometers wide, and has gradually narrowed down over time to somewhere between 8 and 18 kilometers, still surrounded by buried, steeply dipping faults, at least some of which are almost certainly still active today. To really appreciate just how crowded this particular stretch of ocean floor actually is, northern Cascadia is one of the only places on Earth where 4 separate tectonic plates, the Pacific, North American, Juan de Fuca, and Explorer plates, all meet within roughly 300 kilometers of one another. That's the exact neighborhood where Sunday night's earthquake happened. A study that mapped the tearing about 10 months before that earthquake, a research team actually finished mapping what's happening directly underneath that crowded neighborhood. In September of 2025, a team led by geologist Brandon Shuck at Louisiana State University published a study in the journal Science Advances, describing slab tearing in a segmented style of subduction shutdown, driven by the region's transform faults. The method behind that research is worth explaining briefly, because it's exactly how we actually know any of this. The underlying data came from a 2021 survey called the Cascadia Seismic Imaging Experiment, carried out aboard the research vessel Marcus G. Langseth. The ship towed a hydrophone array roughly 15 kilometers long behind it, sending sound waves down into the seafloor and carefully recording the echoes that bounced back up. It's essentially the same basic principle behind a medical ultrasound, just scaled up massively to image fault structures buried kilometers beneath the open ocean. What that particular survey revealed was 2 active tears splitting the plate apart directly beneath the northern Cascadia margin. This tearing is happening entirely inside the slab that has already moved underneath North America, the section now being dragged steadily downward under its own weight. The imaging showed a vertical offset of about 5 kilometers, roughly 3 miles, where one section of the slab has shifted downward relative to the section sitting right beside it, along a structure stretching about 75 kilometers in total length. It's worth being genuinely precise about that 5-kilometer figure, because it's been badly misunderstood elsewhere online. That offset did not happen during a single earthquake. It built up gradually, over an enormous span of geological time, as the plate slowly bent, cracked, and gradually came apart piece by piece. Nobody actually watched 3 miles of rock suddenly drop in an instant. And if a headline somewhere made it sound that dramatic, it genuinely misled you. Along this same 75-kilometer fault, some sections remain seismically active, while other sections have gone completely silent. In most areas of earthquake science, a silent fault segment is exactly the one you'd normally worry about, since silence usually means stress is quietly building up somewhere with nothing there yet to release it. Here, though, researchers are actually reading that silence the opposite way. These particular quiet zones most likely mark places where the slab has already become fully detached from its neighbor. It isn't building up stress there simply because it's no longer mechanically connected to anything on the other side of the tear. Schuck described this overall process in a way that's honestly hard to improve on, comparing it to watching a train slowly derail one car at a time. A gradual progressive breakdown happening in distinct stages, rather than all at once in one catastrophic moment. Researchers have started calling this general pattern episodic termination. Northern Cascadia's subduction system isn't collapsing in one single dramatic event. Nature's own scissors. Transform faults act almost like a set of natural scissors, slowly cutting the larger oceanic plate into smaller and smaller individual pieces over time. Over the last several million years, motion along the Nootka fault zone has allowed the crust to tear apart into distinct microplates that now move somewhat independently of one another. Each time one of these fragments fully detaches from its neighbor, it weakens the overall pull generated by the plate's own accumulated weight, the pull that normally drags the rest of the connected sheet steadily downward into the mantle below. Less pull ultimately means slower subduction, which then pushes more accumulated strain into further tearing, which in turn leads to even more fragments eventually detaching, feeding the whole ongoing process forward across geological time. Researchers currently project that the Explorer plate will fully detach within roughly 1 million years, eventually shortening the active Cascadia Subduction Zone by about 75 kilometers, close to 1/15 of its total length. Geologists have long had strong theoretical reasons to believe subduction zones eventually die off in exactly this gradual, piecemeal way, but until quite recently, they had only ever been able to study the aftermath of the process, long after the fact, watching history happen in real time. Off the coast of Baja California, for comparison, researchers have already identified fossil microplates left behind from the Farallon plate, a massive slab that subducted beneath North America tens of millions of years ago. Those particular fragments are essentially geological fossils at this point, the preserved wreckage of a subduction zone that had already finished tearing itself apart long before anyone was around to study the process directly. Cascadia is genuinely different because it's actively happening in real time, right now. It's the very first modern subduction zone that scientists have ever managed to image clearly enough to actually watch the individual tiers developing as they happen. And to their credit, the researchers behind this particular study were very careful to add an important caution right up front in their published work. These findings do not change the current earthquake risk facing the Pacific Northwest region. The tearing process itself proceeds at a rate of only a few millimeters per year, slower than your own fingernails grow and far too slow to matter meaningfully on any human timescale. Cascadia remains fully capable of producing earthquakes in the magnitude 8, 5 to 9. Zero range, along with the destructive tsunamis that typically come along with them. Neither alarm nor reassurance is the right read. Schuck has deliberately framed this whole discovery as offering useful perspective, not raising alarm. A gradual shutdown that plays out gradually over roughly 1 million years does absolutely nothing for someone actually living in Victoria this particular year. But the opposite claim, the idea that this tearing somehow means the big one is now imminent, is equally wrong, and for essentially the same underlying reason. The tearing changes the internal structure of the plate. It does not change the actual timing of when the locked megathrust fault might eventually rupture. What this fragmentation genuinely does mean is that the northern margin is structurally far messier than the simple two-plate model most people learn about in school actually suggests. There are more internal faults present, more independently moving blocks, and more possible pathways for stress to gradually build up and eventually release somewhere along the system. The fault everyone actually worries about, which brings us to the fault that people are actually genuinely worried about, the Cascadia megathrust itself. That fault runs for roughly 1,100 kilometers, from Northern California all the way up to Vancouver Island, passing directly beneath several million people along the way. Along most of its total length, the Juan de Fuca plate is being steadily pushed beneath North America at roughly 40 millimeters per year. The interface between the two plates stays fully locked at depths shallower than about 30 kilometers, meaning the two plates aren't actually sliding past each other there at all right now. They're stuck together, and strain simply keeps accumulating year after year. The last time this entire margin ruptured in one single unified event was January 26, 1700. which means 326 years worth of accumulated strain currently sits along that fault today. It's assessed by seismologists as being fully capable of eventually producing a magnitude 8, 5 to 9, 0 earthquake. If that eventually happens, a resulting tsunami could reach the outer coastline within roughly 8 to 15 minutes, and worst-case modeling puts potential wave run-up as high as roughly 100 feet in some particularly vulnerable locations. Not the first recent signal from this system. This isn't even the first time the same fault system has made news recently either. Earlier this year, the southern end of Cascadia, off the Oregon coast, produced a slow slip tremor episode of its own. This latest earthquake sits at the opposite end of that same overall structure, and the two ends genuinely don't behave in quite the same way as each other. That's exactly why the Explorer Plate matters so much in this particular story. If the northern segment is barely subducting at all anymore, the accumulated strain currently sitting at that extreme northern tip may actually be somewhat lower than what's already built up along the central and southern portions of the margin. That's a real, if fairly narrow, nuance in how overall risk is actually distributed along this fault system, and it genuinely deserves more precision than it usually gets in casual news coverage. The study's authors also raised a second possibility that could cut in either direction. These detached, fragmented sections of crust could potentially act as partial barriers, slowing or redirecting a future rupture, rather than making it meaningfully worse. If that turns out to be accurate, a full 1,100-kilometer rupture running cleanly through the entire margin in one event might actually be somewhat less likely at the northern end than a simple model would otherwise suggest, which could make a smaller, more segmented rupture comparatively more probable there instead of one single giant event. That particular idea remains genuinely speculative, and it's fair to label it clearly as such, but it's speculation that's at least consistent with the published underlying mechanism. Researchers at the Cascadia Region Earthquake Science Center are actively working these newly discovered structures into their ongoing hazard models right now. Could this be a foreshock? Now for the question this whole event actually raises, and it genuinely deserves a real, honest answer instead of a comforting one. Start with something most people simply don't know. An earthquake can only ever be officially identified as a foreshock after a larger earthquake happens nearby afterward. Foreshocks only ever exist in hindsight. There's no physical property, no telltale signature hidden in the waveform, no distinctive depth or mechanism that reliably separates a foreshock from an entirely ordinary earthquake at the exact moment it actually happens. That isn't some limitation of our current instruments. It's simply an inherent property of how earthquakes fundamentally work. And specifically, the chance that an earthquake gets followed by a magnitude 5. 0 or larger event rises steadily with the size of the initial quake, from under 1% for something around magnitude 3, up to about 6. 5%, give or take a couple of percentage points, for something around magnitude 5. In plain, simple terms, roughly 19 out of every 20 moderate earthquakes are never followed by anything larger at all. That's the honest number, and it's genuinely reassuring on its own. But notice carefully what it isn't. It isn't 0. The technically correct answer here isn't no, it's probably not. And there's a genuinely recent example that shows exactly why that distinction actually matters. On June 24th of this year, Venezuela was struck by a magnitude 7.2 earthquake, followed just 39 seconds later by a magnitude 7.5. More than 1,600 people died. A larger earthquake directly following a large one is genuinely rare. It isn't impossible, though. The real thing worth tracking. So here's the concrete, practical thing worth actually tracking, instead of just sitting around with vague background anxiety about it. The aftershock pattern itself is the real diagnostic tool available here. If aftershocks stay tightly clustered close to Sunday's original epicenter, out in the oceanic plate itself, this was almost certainly just an ordinary internal event, releasing built-up stress inside a slowly deforming slab, and it's essentially finished as a story. But if aftershock activity instead starts migrating eastward toward the subduction front and the locked interface running directly beneath Vancouver Island, that would genuinely warrant closer attention because eastward migration would suggest stress actively getting redistributed into the locked zone rather than simply dissipating harmlessly right where it originally started. That's something absolutely anyone can check for themselves just by watching how the earthquake activity map shifts over the coming days. A useful, reassuring precedent. There's also some genuinely useful precedent available here, and it happens to be reassuring. Back on April 24th, 2014, a magnitude 6. 4 earthquakes struck this same general region, followed by an extended sequence of aftershocks now commonly referred to as the Nootka sequence. A study published in 2020 analyzed that entire sequence and identified something that hadn't actually been mapped before. An approximately 40-kilometer-long subducted fault located inside the Explorer Plate, just north of the main Nootka fault zone. The largest recorded aftershock, a magnitude 5. 3 arrived about 13 minutes after the initial main shock, roughly 20 kilometers away from it. That collected data showed the subducting plate actually bending downward in a direction nearly perpendicular to the way it's normally supposed to be, sliding underneath the continent, deforming parallel to the margin itself, rather than sliding cleanly beneath it, as expected. Researchers only managed to catch this particular detail because a temporary land-based seismic monitoring network happened to already be recording in the area at that exact time, running for about 9 months starting in early 2014. And it simply happened to be listening closely when that earthquake struck. The genuine takeaway from that entire 2014 sequence is pretty direct and useful. The Explorer plate clearly hosts hidden internal faults that are fully capable of producing significant earthquakes on their own. Those particular faults tend to be steep, and they slide sideways, and importantly, a magnitude 6. 4 event occurring inside that exact same system, and releasing roughly 16 times more raw energy than Sunday's earthquake did, still did not go on to trigger a Cascadia megathrust event. Could this have nudged the megathrust closer to failure? Which leaves us with the version of the question people are really actually asking underneath all of this. Could this particular earthquake have nudged the megathrust fault even a little closer toward eventual failure? That genuinely deserves an honest, careful answer, not a dismissive one. Every earthquake does change the surrounding regional stress field to some measurable degree. Near any given rupture, parts of neighboring faults can get pushed slightly closer toward failure, while other nearby areas fall into what's called a stress shadow instead, a zone where failure temporarily becomes somewhat less likely for a while. Passing seismic waves can also briefly disturb faults located much farther away, something seismologists call dynamic triggering. Both of these particular effects are entirely real and well documented within the field of seismology generally. But then there's the underlying scale problem, and it turns out to be decisive here. A magnitude 9 earthquake releases roughly 126,000 times more total energy than a magnitude 5, 6 event. The permanent stress change caused by Sunday's earthquake is tightly concentrated around its own relatively small rupture area, measured in kilometers, not in hundreds of kilometers. The locked Cascadia megathrust, by contrast, extends for hundreds of miles in total. A small localized stress shift occurring at one narrow end of that enormous locked system simply doesn't meaningfully load the rest of that entire structure. If the megathrust fault really is sitting close to eventual failure, it's close because of 326 years of steadily accumulated strain building up at roughly 40 millimeters per year, not because of one single moderate sideways slip happening out in the oceanic plate. The overall stress budget behind a future magnitude 9 earthquake simply isn't built up out of individual magnitude 5, 6 events. What's actually left standing? So strip away both the unnecessary alarm and the false reassurance, and here's what's actually left standing at the end of all this. The Explorer plate is being dragged steadily downward beneath North America, while simultaneously being pushed and sheared sideways by everything surrounding it on every side. Because different parts of it move at different speeds and in different directions, it's being forced to deform internally. On Sunday night, one of its many steep internal fractures simply built up more stress than it could continue to hold, and it broke. That's most likely just the normal expected signature of a plate slowly coming apart over geological time. Not a countdown clock ticking toward disaster. The genuinely unsettling implication buried in all of this isn't that the big one has somehow already started. It's narrower and honestly stranger than that. We can now image the northern end of Cascadia in enough real detail to actually watch it slowly disintegrating piece by piece over time. We can even project that entire process forward roughly 1 million years into the future. But we still genuinely can't say for certain what this fragmenting structure will actually do to a rupture that might start tomorrow. These particular tiers might end up acting as natural barriers, slowing or even stopping a megathrust rupture from spreading further north. Or, alternatively, they might end up acting as boundaries where an entirely new, smaller segmented rupture actually begins instead. So the real open question here isn't really whether Cascadia will eventually rupture again someday. It's whether the most heavily fractured part of the fault system ultimately turns out to be the safest part of the whole system, or genuinely the most dangerous one. Right now, honestly, nobody has a confident answer to that particular question yet. 3 things worth watching. 3 specific things will move that answer forward meaningfully over time. First, which direction the aftershocks actually migrate over the coming days. Clustered activity means routine and essentially finished, while activity moving eastward means everyone should pay closer attention. Second, whether refined location data eventually manages to tie this particular rupture to one specific mapped fault structure, something that took researchers years to properly sort out after the earlier 2014 sequence. And third, whether updated hazard models coming out of the Cascadia Region Earthquake Science Center end up treating these newly discovered tiers as barriers that stop ruptures from spreading, or instead as points where entirely new ruptures could actually start, because that particular distinction genuinely changes how risk along northern Cascadia ultimately gets communicated to the general public going forward. In the meantime, the practical lesson here is honestly the exact same one Peru delivered just 48 hours earlier. A magnitude 5. 6 earthquake is not automatically harmless just by definition alone. What actually decides whether a given earthquake becomes a minor news footnote or a genuine human disaster comes down to where exactly it happens, and what happens to be built on top of it at that location. Sunday night, the answer here was simply open ocean and nothing else nearby. This time, that was purely a matter of geography and nothing more than that. If you want to actually understand what's genuinely happening underneath the Pacific Northwest right now, instead of simply reacting to scary headlines online, subscribe now, because we'll be tracking exactly how these aftershocks continue to move over the coming days, and I'll bring you a real update the moment there's actually anything meaningful to report.